case, you might not have ID versus VDS characteristic flat for JFET after VDS set, which means that you might not have a zero slope beyond the saturation point. So what it means is that you see after you cross this VDS set, this is your VDS set, transition point between the ohmic region and the saturation regions. Once your transistor is biased beyond this VDS set for the given VGS, which is over here like this, for any given VGS. So what happens is that your ID becomes independent of VDS. Okay, and I mean in the expression of the current, the drain to source current, you don't have VDS. But what happens practically in non-ideal cases that you might have your channel being modulated by VDS, okay, and which is indeed the case. So this VDS is, I mean, there's the horizontal electrical field due to VDS, which means the channel resistance is being also affected by VDS. Therefore, it's in a more practical or a non-ideal case, you might have a non-zero slope. Okay, yeah, so it could be like this. It could be like this, which gives an idea of the forward resistance in JFET devices, just like in MOSFETs. Okay, so what happens is that if you look at this expression, this is the actual expression for the JFET device. Okay, this is for the actual. This happened in the actual JFET device. This is non-ideal current drain to current drain source current voltage relationship. Okay, this is an actual drain source IV characteristics. So if you want to find the output resistance R naught, that can be defined as the derivative of ID with respect to VDS for the inverse, because this is in amps and this is in volts. So you take the inverse, it will become volts over amps. So this is ohms for the given VGS. Okay, so what we are doing is that for any given VGS, we are going to find the slope of this curves for which is the reverse. Okay, so the slope, for example, over here is your delta ID for the given rise in ID by the whatever the run you have for the VDS over here. Okay, so it's the ratio of this for a very small increase in ID for a small increase in VDS. Okay, so if you consider this expression over here, this gives the forward resistance of the JFET device. So this non-zero slope can be described through the following equation. You take the derivative, substitute this equation into this one. You substitute this equation for the slope of IV characteristics, and then you find that this is equal to lambda IDSS 1 minus VGSQ over VP, and this is precisely the drain to source current at the given Q point. Okay, so this is IDQ. Therefore, R naught is given by 1 over lambda IDQ, where lambda is the channel modulation parameter. So this is here modulating the channel. So this is channel modulation parameter. So in fact, for a non-zero channel modulation parameter, if this is 0, then you have the ideal case. Okay, so this is modulating the channel. So if the lambda is 0, you don't need to even consider this. Then the case is again ideal. Okay, so to consider this non-ideality, which is non-zero IV slope beyond saturation, the channel resistance is also being affected by VDS. That means VDS is also controlling the current, the flow of the current, the drain to source current ID. Okay, so if you consider this, then there is a forward resistance which is given by 1 over lambda IDQ. So in case of MOSFETs, now if you recall, in enhancement mode gallium arsenide MOSFETs, they can be fabricated with the current IV characteristics like those in enhancement MOSFETs. Therefore, they have a very similar relationship for saturation and non-saturation. And therefore, for ideal enhancement MOSFET based in the saturation region, we can write ID. Kn again is the conduction parameter, VGS is the gate source voltage, VTN is the threshold voltage. So your saturation, the current in the saturation is again not dependent on VDS. And this is the ideal cases. Okay, so this is ideal case. This is the ideal saturation. This is again ideal enhancement mode, non-saturation region. So in non-saturation region, since your Current is increasing with VDS before it reaches VDS sat, after which the transition point for the given VGS, current stays constant for the given VDS. So the relationships you find for MOSFETs are very similar to what we have already considered for MOSFET devices. Okay, so there again the similar relationships. The Kn is the conduction parameter, Vtn is the threshold voltage, and which in this case is equal to the pinch off voltage. So for n-channel and enhancement mode MOSFET, you recall that the threshold voltage was positive. That is, you require a certain voltage in order to turn on the device. For depletion mode, it's the other way around. The MOSFET is already on because there is an establishment of channel between drain to source, but you need to apply a negative gate voltage to turn off the device. Okay, but the IV relationships are very similar. For this, you can use this IV relationship for MOSFET, just like we did for MOSFET. But for JFET devices, this is given by 1 over 1 minus VGS VP, so it's a little different. Okay, these are for JFET devices. This current port relationships are for JFET devices. So that's all for the IV characteristics of JFET and MOSFETs.